Hey guys, this is Chrissy, and I am coming to you with our second installment in our series, Not the Ideal Medium for Teaching Physics. In the previous chapter, we were talking about light's wave nature, how it interferes, interacts with films, and its behavior in slits. We called this the wave model of light. While the wave model explains a lot, like interference patterns formed as light passes through a slit, it doesn't explain other behaviors, like how mirrors work. For this, we want to use the ray model of light. Under this model, light behaves like a particle. This theory assumes that these particles travel in a straight line, are emitted from all points on an object, and that they have the ability to reflect, scatter, and absorb. We'll start by talking about reflection. This is when light bounces off a surface. The law of reflection states that light will bounce off a surface at the same angle that it came in at, or theta I equals theta R. This says that the incident angle, or the angle of incoming light, is going to be equal to the reflected angle, the angle of outgoing light. Note that the angles that we're using are with respect to the vertical, not the surface. So they're between the vertical and the ray. Let's try an example. If your height was h, what is the shortest mirror on the wall in which you could see your whole image? So let's start out by drawing it. So we have you, we have the wall, and we have our mirror. First thing that we're going to do is we're just going to draw some lines to keep us straight. First line is going to go from the top of the head out. I'm gonna make that a little bit shorter. So top of the head out. Next is gonna go from the eyes straight out, straight across. And the last one from the feet straight out. We want the smallest mirror possible that's going to show the person's whole body. If we want the smallest one possible, then that would mean that we want the top of his head, the light from the top of his head to hit the top of the mirror, light from his feet to hit the mirror, and both of those, right after they hit the mirror, they're going to go to his eye. Let's draw out those light rays. So top of the head, it's going to go to the edge of the mirror, the very top of the mirror. It's then going to bounce off with the same angle and hit the eye. Then from the toes, we're going to do the same thing. It's going to hit the bottom of the mirror, reflect off, going to the eye. We now have this. This is showing his entire body. We had stated before that our guy is of height h. So our guy is of height h. Let's call this distance here, from the top of his head to his eye, we're going to call that L1. Then from his eye to his feet, we will call that L2. We know something interesting about these. Since they're bouncing off at an equal angle, we actually know that they're cutting it in half, which means that this distance here, so from the top of the head to where the red hits, we can say that that is L1 over 2. That's half of that distance, which means that the rest of it from the mirror down is L1 over 2 as well. So if it hits the mirror at the exact top point of it, that's halfway down. I didn't draw that exactly right, but that's what we're trying to look at. We can do the same thing for L2. So we have the mirror. So from here down to the mirror, say that's L2 over 2. And this here is L2 over 2. H is equal to L1 plus L2. That's just what we have over here. Oh, H is L1 plus L2. The mirror length that is L1 over 2 plus L2 over 2. So the mirror length is equal to L1 plus L2 over 2, which is equal to H over 2. The implications of this are that for you to see your whole reflection in a mirror, the mirror has to be half your height. You'll notice that one thing that doesn't even play in here is the distance from the mirror. It doesn't matter how far away you are from a mirror. So long as it's half your height and at the right spot, you'll be able to see your full reflection. Distance from the mirror does not matter. We were saying that this model explains mirrors, so let's take a look at that. When looking at a plain mirror, just a normal flat mirror like you'd have in your bathroom, you see an image on the other side. The way our brains work, it assumes that all light is traveling in a straight line. It doesn't account for turns or bends. If we have an object in front of a mirror, I'm going to call it the dot of sorcery. The light will hit the mirror, and then it will go to your eye. Your eye will trace back the reflected image in a straight line, and the dot of sorcery will appear behind the mirror. When you see an image behind a mirror, we call that a virtual image. This is when we see an image at a point where no light actually reaches. When labeling this diagram, we'll say that S is the distance between the object and the mirror. And S prime is going to be the distance between the mirror and the image. Take a look at example 2. It's 165 centimeters from your eyes to your toes. You're standing 200 centimeters from a tall mirror. How far is it from your eyes to the image of your toes? We're going to start by drawing out the picture. We have your evil twin on one side and you on the other. You are 200 centimeters from the mirror, and your twin is 200 centimeters away as well. And you are 165 centimeters tall. Light is going to bounce off your feet and into your eye. This is going to create the ray that your eye traces back. That's the distance that we're looking for, and we will call it R. R is the hypotenuse of a triangle. We have your height here. I think we're assuming that your eyes are on the top of your head, which, whatever. So we have your height here. That's 165. And we've also got this here. So we get the triangle from here. We can just use the Pythagorean theorem. So if this is x plus x prime, and this is y, we have that r squared is equal to x plus x prime squared plus y squared. R is equal to 200 centimeters plus 200 centimeters squared plus 165 centimeters squared, square root of all that. And we get that R is equal to 433 centimeters. There are two types of reflection. The first is called diffuse reflection. This is when light bounces off an object, but is scattered in many directions. This causes dull reflections, like if you had crumpled up aluminum foil. These dull reflections are due to imperfections in the surface. A flat mirror is what you usually think about with reflections. This is a smooth surface that produces clear reflections. This is like what you have in your bathroom mirror. I'm going to end part 1 here, and I will see you in part 2.